Okay, so we're going to take a look next at the Moore machine. So the counter is a special case of the Moore machine. So I have the same counter diagram back again here. And we're just going to have to make a couple modifications to generalize it to the Moore finite state machine. And so the first change here is going to be, no, I didn't want text. I said go to the selection. I must not have clicked it somehow. So we're again going to have combinational logic, and we're going to have memory. And so we're going to make a couple slight modifications here. So the memory, it will remember, in this case, remember what our situation is in general for a general Moore machine, for a general finite state machine. So we're going to remember what our situation is, and then sneak this out of the way. And what we described for our combinational logic is also going to be slightly different. So this is the combinational logic controls how we track the situation. We'll phrase it that way. Okay. This time, for this particular example, it will be 3 flip-flops this time. But we haven't determined that yet, actually. But it will again be based on JKDT and the relevant cues. Now this time, unlike with the counter example before, and you can have a control line with counters as I mentioned, but in this case we definitely have an input X. So we have an external input, and our input is X. So an input's coming in here, and both the present state, what the memory is holding on to at any given moment, as well as the external input will be factored in to control what we remember about our situation. So depending on the value of X, we may get an input which makes progress toward the sequence that we want to find. I haven't mentioned the problem here, but this is another sequence detector. And so we need an output Z which produces a 1 when X receives this sequence 0, 1, 1, 1, 0, 0 in order one at a time. And if we have not observed this sequence of 6 digits, we want Z to be 0. So our memory needs to remember some amount of information about the past inputs in order to determine what the output should be. And so it's going to remember some information, and that information runs back in combination with the external input to determine what our memory needs to remember after the new data enters in. So we have this feedback system here. But we also need to add a special output. So instead of the output being just the contents of the memory 1 bit at a time in a raw format, the output in a general Moore machine has a separate block up here, and so then we have output combinational logic, and specifically in the Moore machine, the output logic, which in the end is going to produce that's not nearly wide enough. Let's fix that. Yeah. So the output logic is going to produce our output. In this case, we call it Z. But the output Z is going to come from output combinational logic But in a Moore machine, the output combinational logic is only allowed to observe the Q values, is why I've drawn it as a separate block. If it wasn't for that restriction, we would be able to draw it in a single combinational logic block. But for a Moore machine, we can't do that. So the output combinational logic is only allowed to observe the present state. This subset of the logic is not allowed to observe the input X in computing the output. However, the input is allowed and necessary in the portion of the combinational logic that controls J, K, D, T, etc. Because we need the input to change the contents of the memory. But in the Moore machine, our output needs to be a function only of the contents of the memory. The output is not allowed to observe the input in order to make its decisions. With the Mealy machine, that restriction is removed, and the output combinational logic is the same type of logic. It's also allowed to observe the input X. So in the Mealy machine, we'll fold this into a single block, and the output will be allowed to come from general combinational logic in a Mealy machine, whereas for the Moore, the combinational output logic portion can only observe the Qs. So here, I sat down and constructed this big table with a bunch of colors because I thought it might help clarify this. So this table that I've constructed is specific to this type of problem, the sequence detectors we've been looking at. So I wanted to break it down in terms of what are the decisions we have to make as we design this machine. So I'm going to run through this table one step at a time. So here at the top, I've written that we're trying to generate a Moore machine sequence detector for the code 011100. All right, and we would like to do this as efficiently as we can. So in theory, yeah, there is a Moore machine which would have 6 flip-flops, and the 6 flip-flops would be in a shift register format almost, and you would keep track of the numbers, and then you would have logic that just checks all 6. Now, there's something closely related to that would work, but we don't want to head down in that direction. We would have issues, however, because the shift register would require the contents to be pre-filled with 0s or 1s, and that would throw off our data analysis. So that's the reason that we can't get away with so easily with manipulating a 6-bit shift register into working. There's a way to do it, but you would have to get around that issue. So we're going to do this from first principles using a similar type of design process to the counter. Okay, so our sequence detector is 011100, and there's always a little bit of thinking about, well, what are the states that this machine needs to have to be able to do the thing we're asking it to do? And so here I've defined 7 states, because one fairly natural way to define our states is sort of, in this case, specific to the sequence detector. We have a state for each number of correct digits we can have. So we have a state for when there are no correct digits. We have a state for when 1 is accurate, 2, 3, 4, 5, and 6 accurate digits out of the possible 6. So I've named these states A through G, which are just arbitrary names, but they sort of imply an order. A comes before B, before C, before D. So as we make progress, we advance from A toward G, and if the input takes us further away from our sequence, we may have to drop back down. So the chosen flip-flop code, as I've mentioned before, is arbitrary. We can make this work we can assign A to any code and B to any other code and C to any other code, and it would work out just fine. Now, it's fairly natural to assign A to the smallest binary number and G to the largest out of the list and just file them in order. So that's what we're going to do. When you design it, we will be designing in terms of the names, and it will not actually matter what the underlying code is until we go to the final implementation details. So we don't really have to worry about this right now, but I wanted to point it out here because I've assigned 0 to no correct digits and a Q code of 1 to 1 correct digit, etc. So that's why this is sort of a natural choice. But what's important is that there are the certain number of correct digits, and I'm going to cast that as, well, since the data comes in serially, no correct digits means there's nothing useful. So that's my short description over here. And to have 1 correct digit, the only thing that can really mean, because it comes in sequentially, having 1 correct digit means we have had a 0. The most recent input was a 0, and that is the first digit in the sequence. So we have 1 correct digit. We will complete the sequence if the following 5 digits are 11100. And so that's why this gets to be its own state. We have a state for when we've got a 0 most recently, because that means we'll be done if we follow it up with 11100. Then we have state C, where we have 2 correct digits, and those digits have to be the 0 and the 1, because the data comes in sequentially. So if we have 0, 1, the first 2 digits that we need are in place, and if the serial input hands us 1100, we will complete the sequence. So we continue this process, and 3 correct digits means we need the first 3 digits as the most recent inputs, so that the next 3 might take us all the way to the end. And we advance all the way through until the full sequence of 6 has been observed in order. So this is when we have observed 0, 1, 1, 1, 0, 0 in order. At that point, we can activate our output, and at any other circumstance, our sequence has not been completed, and our output must be a 0. Because this is a Moore machine, and the output is only a function of the present state, we output a 1 while we sit in state G, which is the state we go to after 0, 1, 1, 1, 0, 0 have been observed in order. And as long as we sit in G, our output should be a 1. And if we're sitting in any other state, our output should be a 0, because while we're in these other states, the sequence has not been completed. So once we've set this idea into motion, I've added this new little detail here, which is our state criteria listing. Okay, so we'll start all the way down here at G when we've got 6 correct digits in a row, and we can express that condition as the last 6 inputs having been 0, 1, 1, 1, 0, 0. If we meet that criterion, it doesn't matter if we meet any of these lesser criteria. I'm trying to be very careful with my conjugation of criterion. And if we have most recently observed 0, 1, 1, 1, 0, 0, I've written in yellow the other possible criteria we're interested in. So were the last 5 digits 0, 1, 1, 1, 0, If the last 6 digits were these, the last 5 would be, if we're in state G, the last 5 would be the 11100, which is not the same thing as 01110. So we would not meet that. But we don't really care whether we meet it. If we meet the 6, we go to G. Oops. And it doesn't matter if technically it also fits the rules for F, E, D, C, B, or A. If we can go to G, we go to G. And if you check the last 5 digits, the last 4, the last 3, or the last 2, even the last 2, 0, 1 is not the last 2 digits, so we wouldn't meet it. Technically, the criterion, the last input was 0, is met in this situation. If our last 6 were these 6, the last one would be 0, and we would meet this criterion, but it doesn't matter because we meet the more interesting criterion that all 6 are these. So I marked the ones after the yes in yellow because while we can check that criterion, checking it doesn't change what we're going to do. So to be in state F, we are only allowed to be there if the last 5 inputs were 0, 1, 1, 1, 0. And this needs to be its own state because in that situation, we are just 1 digit away. If we're in F and our input is a 0, that will take us to G because the final 0 would complete the sequence. We also need this criterion, the last 4 inputs are 0, 1, 1, 1, because if that's the case, we will make it to G if we get a 0, 0. And so that's why we set the states up in the way that we do, because of what this machine has to keep track of to ensure that it will know when all 6 digits are in place. At any given moment, all it actually needs to know is what are the last 6 digits, what are the last 5 digits, what are the last 4, the last 3, the last 2, and the last 1. And we compare those digits to the beginnings of the sequence. So we just look at the last 6, and if the last 6 are accurate, we meet the criterion, we go to state G. If we fail, our last 6 are not these 6, we then need to check, are we 1 step away? So we compare the last 5 digits to this. If we meet it, we are in state F because we're 1 step away. That's what F means. The last 5 digits are ready for when we get that last 0, we would complete our sequence. If we fail the 5-digit check, we should then do the 4-digit check. If our last 4 have been 0, 1, 1, 1, we're just a 0, 0 away. And so we need to remember that we're 2 away. And so we just run this process back. If the last 3 were these, we're 3 digits away, so we'd better remember that. If our last 2 are 0, 1, we're 4 digits away, so we'd better remember that. If our last one was a 0, we're 1 digit away, or we're 5 digits away, sorry. So we need to know that. And if we fail all of these 6 criteria, we say that we have no progress. So there are a lot of ways to have no progress, but these 6 checks are the ones we have to make, the only ones we have to make to keep careful track of this sequence. So this machine is going to forget previous digits. If we give it the wrong digit, it's going to forget past digits that can no longer help us by running through the checks in order from 6 down to 1. and it will just check, how many digits do I need to remember? It only needs to remember a sequence of digits if it is the correct sequence of digits to line us up to be closer to completing the sequence. So off to the side here, I then said, okay, in order, if we're in this state, we need to determine what will happen if we get a 0 as an input at that point, and we need to determine what will happen if we get a 1 as an input at that point. And this is great prep to, we will draw the state diagram in just a moment. Okay. So up here, if we're in state A, we have, well, okay, wait, let me pause for a second. Actually, I'm going to cut it here because I'm going to start drawing the state diagram at the same time. So this is where I'm going to cut it then, and we'll continue in the next video.